Hi, my name is Doug Natelson. I'm a professor at Rice University in physics and astronomy, and I'm going to talk to you now about tunneling spectroscopy of C-axis epitaxial cuprate tunnel junctions. First, I want to say that this work could not have been done without my students, Pan Zhao and Liang Chen, our collaborator Ilya Sochnikov, my local theory collaborators, Professor Matt Foster and his student T.C. Wu, and none of this would have been possible without the outstanding epitaxially grown oxide samples from Ivan Bozovich's group at Brookhaven, which includes his postdoc Jihei and his longtime collaborator Tony Bollinger. This work was supported financially by the U.S. Department of Energy Basic Energy Sciences. It was supported also by the Welch Foundation and the Moore Foundation. So let's talk about superconductor insulator superconductor tunneling. If you have a conventional metal, its density of states is pretty boring, and then you've got some filled states, and then you've got a Fermi level and some empty states. And as you go through the superconducting transition for an S-wave, conventional S-wave BCS superconductor, you open up a gap at the Fermi level, and the gap is of size delta, and there's no quasiparticles allowed in here, particularly if you're at t equals 0. And you have these filled states and the empty states again, and now you've got this coherence peak. You've got this square root singularity from the BCS density of states. And this is a density of states that purely looks at energy. It ignores momentum conservation and tunneling and all those issues. It also ignores coherent processes. There's no Josephson current we're worrying about here, or Andreev reflection or anything like that. When you use this density of states to model tunneling, this is sometimes called the semiconductor approximation. That's what Tinkham calls it in his big book on superconductivity. Now, if you want to understand the differential conductance of a SIS junction, you want to ratchet the densities, these densities of states past each other. So at zero bias, you've got no conductance because the filled states line up entirely with the filled states and the empty states with the empty states. As I apply a little bit of bias, at first, again, you see no conduction because there are no empty states allowed in the gap over here for these filled states to tunnel into. When you first line up these square root singularities, you get a big peak in the differential conductance. This is called a coherence peak, and it's at a bias. It occurs in an SIS junction at a bias of twice the gap energy divided by the electronic charge. And if you keep going, you complete this full shape of the differential conductance, and this is close to what is actually seen in model BCS systems, S-wave superconducting systems like this vacuum lead tunnel junction, well below TC. Now, D-wave systems like the cuprates are more complicated. So what we have here is a plot of sort of the band structure of a D-wave and a kind of a BCS idealized D-wave superconductor. What you see is that the gap has nodes, and at these nodes, even at t equals 0, you have Dirac-like nodal quasiparticles here. This is, again, the theory of a D-wave superconductor. So what should that show you in the terms of the density of states for tunneling? Well, the quasiparticle density of states still has this coherence peak, but it no longer goes sharply to 0. Instead, you've got, because of the nodal quasiparticles, you've got something that trails down and eventually hits 0 at 0 energy. And if you do the analogous calculation for that, again, ignoring momentum conservation, ignoring worries about coherent processes, your expectation for what the tunneling differential conductance should look like, normalized by the normal state conductance, looks like this. And in fact, as you go to t equals 0, this is temperature in units of Tc, I should say. As you go to t equals 0, the zero bias conductance will fall all the way to 0 in the theory model, and you will still get coherence peaks that happen at basically twice the gap energy divided by the electronic charge. Now, the junctions I'm going to talk about here were grown by atomic layer by layer epitaxy by the team at Brookhaven, and they consist of lanthanum, strontium, copper oxide. We work with 4 different doping levels. A tunnel barrier, it's a little bit unusual here. The tunnel barrier is the Mott insulating parent compound, lanthanum cuprate, La2CuO4, and we have as little as 3 monolayers or 1.5 unit cells of this stuff, the undoped compound, and then we've got more LSCO on top. So even this thin a barrier shows no pinholes, no supercurrent, as we'll see. Here is a cross-sectional scanning transmission electron microscope image of such a device. The group at Brookhaven's been optimizing these structures for many, many years, and they are really structurally incredibly nice. So in some sense, these devices should be sort of a test case. you've got tunneling in a structure that is so structurally sound that the only disorder you really expect to be in there predominantly, you don't expect it to be impurities, you expect it just to be from the doping, the intrinsic disorder due to the doping in the LSCO layers. All right, so you can take these stacks and you can etch them and make mesas, and you can make tunnel junctions, and you can independently contact the bottom and the top top LSCO layers. And if you go and you do that and you measure differential conductance, what do you see? Here's the raw data for 4 different doping levels. I've indicated the doping levels and the transition temperatures for each, and the x equals 0.15 is the close to optimal doping. So what you find is there's a clear V-shaped background. That's usually ascribed to the pseudogap. There is also an asymmetry in the tunneling conductance. Conductance is always higher when the electrons are flowing from the bottom LSCO electrode to the top. That's actually consistent with expectations of this polar material, the way it's grown, and the gradient in epitaxial strain as you move away from the growth substrate. Now, what does this look like when you normalize to the normal state conductance at, say, 50 Kelvin? Well, a few things should jump out at you. First, as I said, there is no supercurrent. This is true even if you make the barrier even thinner. This tells you there's no pinholes in the barrier, but it also violates the typical Embagoakar-Baratov expectation for standard tunnel junctions, where the critical current times the normal state resistance is usually on the order of the tunneling gap, of the superconducting gap, rather. Well, since our critical current is basically 0, we violate that relation maximally. Also, you should see there is a large residual zero bias conductance. Even down to dilution refrigerator temperatures, it doesn't really change much below the 2 Kelvin data shown here. The zero bias conductance remains at about 25 or 30% of the normal state conductance. That's very surprising given the expectations I just told you. Also, you can see, in addition to that, the gap sort of being filled in a bit, there's very, very strongly suppressed coherence peaks. Only in the optimally doped case do you see anything that looks like some kind of coherence peak left over. So this is all rather surprising given the structural perfection of these devices. How can we try to model this? So if you assume a BCS type D-wave superconductor, so this is just a model that we're going to apply, this is what the idealized quasi-particle density of states looks like in that model. You've got the square root singularity here in the denominator. You've got the D-wave angular dependence in the xy plane. You can average over that. So as I just got done telling you, this does not do a good job of modeling the data. This also, again, ignores momentum conservation. So what happens if you, how do you deal with this? Well, we can take an approach that people have been taking since the late 1970s, led by Bob Dines, to try to understand why there might be, say, residual quasiparticles in the gap. You can insert a lifetime broadening term here, this gamma term, which is sometimes called a Dines parameter. I should say, anytime you're doing this, you're already deviating from conventional BCS. So what does the Dines parameter do? Well, it suppresses coherence peaks and it fills in the gap. Now, can you do that in a consistent way and fit the data? It's a little bit tricky. The attempt we use an ansatz that was, for example, already employed by Seamus Davis's group to look at tunneling data in BISCO, where this lifetime broadening parameter has 2 pieces to it. It's got an energy-independent piece, beta, which is sort of what Dines originally used, and this is often introduced as a pair breaking rate, and as done in ARPES, for example. And this second term, this first term here written here that has the omega dependence, the energy dependence, that is structurally credible from scattering of nodal Dirac quasiparticles off quench disorder. But again, this is an ansatz that we try to use. So what happens? What does this do? Like I said, it suppresses coherence peaks. It fills in the gap. How does it do up against the actual data? Well, it's not too bad for the optimally doped case. You can pick parameters and at each temperature, and you can do a pretty good job of fitting the normalized tunneling spectra. What you find typically, like in other Dines superconductors, the gap doesn't really go to 0 at TC. Instead, what happens is the lifetime broadening blows up as you get towards TC. Other people have seen similar things when trying to understand ARPES data in the cuprates. Unfortunately, this ansatz really just does not work well for the underdoped devices. It's very, very difficult, even if you've got both alpha and beta to play with, it's very difficult to get the shape right, to get both the suppressed coherence peaks and the residual zero bias conductance in a kind of a compatible way. So that's pretty much the main upshot of this work. is that I've got some supplemental slides, but I won't show them in this online presentation. It is surprising. We have epitaxial clean junctions that should be archetypes of what you expect for tunneling in clean C-axis D-wave tunneling. And in fact, you might even imagine that you'd have transverse momentum conservation in such structurally nice devices, but you apparently don't. The tunneling spectra are not well described even by simple extensions to BCS. You've got extremely suppressed coherent tunneling along the C-axis. Maybe the tunnel barrier is doing something non-innocent here. There are greatly suppressed coherence peaks and large residual zero bias conductance. So that's it. That's where we are. We are trying to understand this better. And with that, I will put up my acknowledgments again, and thank you for your attention.